hope that's clear. So there are three types, three places where you can use the cache: database, front end, and back end. So in case your front end server makes a lot of requests to the back end server, put a cache here so that the front end doesn't have to always call the back end, takes the information from the cache. Back end server does not have to always make a request to the database. It can always make a request to the cache instead. So that's the three places you can use the cache. Now comes scalability. So we are in a session by Scalar. Scalar, where you think about scale of products, right? So scalability is something that you have to think about when you're designing a system. That's the most core important funda, right? So scalability has three axes: latency, throughput, and capacity. So latency is when you make a request to a server, the response that you get, the delay before you get the response is the latency. So the more the latency, that means the more it's taking, the more time it's taking to respond to you. The less the latency, that means the responses are very quick. So you want less latency, okay? People confuse this a lot. They think that they want high latency. No, you want low latency because you want as less delay as possible between your responses. You need to have a high throughput. That's basically how much data can pass through the system at any given point of time. So it's like Mbps or Gbps, PBPS, right? How much amount of data can pass at a given point of time, like per second or per minute or per hour. Now, capacity is not bounded by time. There's no per second or per minute. It's an entirety how much data can be stored or how much data can flow through the system in entirety. Okay. Now, what's important to remember is performance is not equal to scalability. Okay. Performance, basically, you can have very low latency and your system can be highly performant. But if it doesn't have the capacity or the throughput, it won't be scalable. So people confuse these two concepts a lot. And in the chat, also, you'll see a lot of people asking me this question, same question. Every session, I get the same question. Hey, what's the trade-off between performance and scalability? Are they the same? Like many questions around that. And even interviewers, they ask you many questions around this. You have to understand performance is a completely different concept. Scalability is a completely different concept. Okay. And these three things are like capacity, throughput, and latency are the three axes of scalability. So scalability, a little bit more about scalability. You have horizontal and vertical scalability. Horizontal basically means you add more servers. So I'll just give you an example, actually, instead of going into the jargon of things. Let's say you have an AWS account. You create one EC2 instance, and you start getting some traffic on your website. Now you want to ensure that your entire system does not go down. What do? You start creating one more EC2 server, and you basically connect all of them to the entire network, and you say, okay, I have all these different EC2 servers, so that even if one becomes overloaded, there are more to take up the load. So that's basically horizontal scaling. You keep adding more and more EC2 servers. Vertical scaling is basically, let's say I have an EC2 server. It's a T2 micro server. And I made a T2 medium, T2 large, whatever I keep making it, like I keep increasing the size of the server. I'm scaling it vertically. Okay, so that's vertical scaling. So you have two types of scaling. Now, to horizontal scaling. So between horizontal and vertical scaling, horizontal is usually the good type of scaling. It's more, it's better. It leads to better results. But there are two laws that get applied to horizontal scaling. One is the Amdahl's law. The other is the universal scalability law. I will quickly explain these to you. These are slightly difficult concepts to understand, but they're also very important. So I always go through these because they can be very important interview questions, and I don't want you to miss out on interview questions, right? That's why you're probably learning all this for. And now, again, this is not just important for the interviews, but it's also important to understand how systems work in the real world. So Amdahl's law is saying, this, by the way, you'll have this presentation after the session, so you can zoom in also and see it properly. But what Amdahl's law is saying that you keep adding these servers, right? So I have these number of processors that keep increasing. They keep becoming double. I will get a speed up in my system. So I will get 2x, 4x, 6x, 10x speed. My system will start getting a lot of speed. But it will all max out at 20x. So more than 20x speed, I get something called as a law of diminishing returns. In the sense, the speed of the system does not increase after that. And even if I add 1,000, 2,000, 4,000, 8,000 servers after that, the speed stops increasing. So this is what happens in the real world. In the real world, You can't keep scaling unlimitedly and keep getting a lot of speed. You have to have, at 20x, the amount of speed up that you get in the system stops, and then you stop getting any results. Now, universal scalability law says that that it doesn't even happen till 20x. So there was the Amdahl's law, then came the Gunther's universal scalability law. He says that even 20x you won't get. You'll just get somewhere around 10x, 12x. So here, this line that you see here, the blue line, that's saying that around 12x, you'll start capping out. You won't get any more speed up above 12x. This was the ideal. It keeps increasing. But this is the actual speed up, the blue one. So why does it happen? It happens because there is something called as a communication constraint and the latency constraints that get added to the Amdahl's law in the real world, which make it, which make the speed up impossible after 12x. So that's important to understand, because when you're working with so many servers, you get communication constraints. You can't communicate with all the servers at the same time. You have to use load balancers, and latency is induced because they have to communicate with each other. So all of that happens. So you don't really get more than a 12x scaling. Okay. Then you can scale with the help of distribution. So you can distribute data in the sense from your application, you store the data in 3 different databases. Or you can distribute compute. You can use 4 different servers to compute the information by dividing them into small parts. Or you can replicate data. So there's a main data store, which is your main database. It creates 2 small replicas so that even if the main database goes down, one of the 2 replicas becomes the main database. So they are all communicating with each other, and then one of the databases, the replicas, becomes the main data store. So with state, how do you scale with state? There are 2 ways. One is the stateful way of scaling, the stateless way of scaling. So stateful server. So when we used to use PHP long back, right? Technologies like PHP, we had state-based servers. So in the sense, you were storing the session information on the server side. The problem is that for the client A being the front-end server or just the client A is making a request to server 1, and server 1 has the data for client A. So if server 1 goes down, client A cannot ask server 2 for the information because only server 1 has the session information for client A. And that's the problem, right? So if client B goes down, client B cannot ask server 1 or server 2 for any information because only server 2 had that information. So that's the problem. Where with stateless systems, you have multiple servers, and all of these servers don't store any session information. All the information is only stored in the databases. So you can use load balancers here, and they can simply redirect the traffic to any of these servers. Now, even if one server goes down, because the servers were not storing any session information anyways, even if one of the servers goes down, the load balancer can send the request from the client to any of the servers, and it'll all work perfectly and smoothly. So stateless systems are better, and in modern system design, we always use stateless. So you just want to understand that modern systems are all about stateless, and we'll be using that in today's system design. This can be a big interview question. Which one scales better, or what is state, all of that stuff. Now you know the answers. Okay, so important topic, sharding. Your databases cannot keep endlessly storing information because they start failing, right? They start going down. You've seen databases getting overloaded, all those problems. So how do you scale databases? You scale them by sharding them. So you create either vertical shards or horizontal shards. Vertical shards, what you do is you divide the columns into different databases. With horizontal shards, you divide the rows in different databases. So here's the original table. The first vertical shard will have first name, last name. Second vertical shard will have the city. So you've divided from the columns. The columns you've divided into 2 different databases. So now it becomes easier to store information. And similarly, you can keep dividing into more and more shards. With horizontal shards, you can store between, let's say, the first 2 rows you store in the first database, and the second 2 rows you store in the second database. Now, obviously, this is an example, right? So many people, they don't understand that I'm just taking an example. So they ask me a question in the chat saying, hey, for 4, this is such a small database, why do you need to do any sharding? I'm just showing you with a small example. It's a small database, but in reality, you would have like thousands and thousands, millions of records probably. That's where you do horizontal sharding, and you'll have thousands of columns. That's where you'll do vertical sharding, right? I'm just showing you using a small example how it actually works. Databases replication. So you have the original database, and it stores information in replicas. Okay, so even if the original database goes down, one of the replicas can actually become the original database. Now the problem here that you need to know that replication sounds like a really good silver bullet. It can solve everything, but it's not the case. You need to know the problems or the cons behind replication of databases. The problem is that it can lead to inconsistency in the system. So whenever there's some new information that gets written from the server to the original database, that needs to traverse through all of the replicas, and all of them need to have like a consensus that this is the new information. So all of them get updated. But if there's some new information in the original database, and before it's able to write information to them, it goes down, it crashes, right? There's an attack on this database. Then that information is lost. And one of the replicas, who now has to become the original database, the main database, will not have that recently written information. And that's when the entire system becomes inconsistent with each other. And that's the problem. So that's the problem with replication. You need to know that inconsistency can occur in the system. So with systems where consistency is of critical importance, like payment, right? You don't want to have multiple payments, or if payment has gone through, you didn't store it in the database. That's a big problem, right? Payments. You might want to refrain from using too much replication, or you might want to have different strategies. Okay. Indexing of databases. So let's say you have a table which has ID, name, and city, and you had sorted by ID, which is auto increment IDs, stored by IDs, and you have name and cities. Now, what if you wanted to be able to search much easier from the table? What if you wanted to be able to search in a better way? What you could do is you could put an index on name. On the name field, you put an index. That means that the data will be organized based on names. So like Andrew, Blake, Day. So from A to Z, we have organized it. Now what happens is that when you have, let's say, 10,000 records, right? And you put an index on the name. Now whenever you search for, let's say, Zach, this guy called Zach, now the system knows that there's an index based on name. So if there are 10,000 records, the first 9,000 records, it does not have to search. Just needs to search the last 1,000 records, or maybe even the last 500 records. That's it. So that's the beauty of using indexes. Otherwise, you would have to go through the entire database, all the 10,000 records, and that'll be very slow. This is why indexing makes searching for data faster. So you've indexed based on the name. SQL versus NoSQL. So with SQL, you have RDBMS systems. We all know what are SQL databases. NoSQL, there are multiple types of NoSQL databases. You have key value stores, you have graph DBs, you have document DBs, and you have column DBs, column stores. Okay. NoSQL databases are horizontally scalable. So like MongoDB, right? You don't have to have a strict schema. Even if there's a schema-less information, completely okay. You don't have to do any painful migrations. In our case, a NoSQL database is going to be very good. We're going to have a microservices system where we'll have like multiple databases, different types of databases with different microservices, but mostly we'll be relying on NoSQL databases because the information that you get from each stock, it keeps changing. That the same number of fields are not there for all stocks. So we want to have something that can work with a very flexible or a dynamic schema. So we'll be using NoSQL databases mostly. Row DBs versus column DBs. So row databases, you store a lot of rows, few rows in the databases. In the column databases, you store, let's say, the ID column in a database or name column in another database, and so on. You can store based on columns. Column databases. So in our system, right, there'll be a service for stock data. So we'll be having like stock related information. And this is usually a read-heavy information. So users are always reading this information, stock-related information. And this is usually a read-heavy system. So for read-heavy systems, you are better off using column stores. Or any other use case, like let's say analytical or analytics engines, creating data visualization, all of that. Column data is really, really good. So column databases are like Cassandra. They're a very good fit out here. Proxies. So you have forward proxies and you have reverse proxies. Proxies, basically, if you're exposing your servers to the internet, you want to hide the IP addresses and the location of your actual servers. So for example, if you have clients who are going to, like make a request to your front-end servers, the location of your front-end servers can be hidden with the help of a forward proxy. Whereas if you have your front-end servers and your other external systems integrated with your servers, you can have a reverse proxy to hide the IP addresses of the backend servers. If the external systems, like external integrated systems, they come to know the location of your, or the IP addresses of your servers, they are going to attack it and get your systems to go down or steal all the information. You don't want that. So this is why you use proxies. Okay. Then you have rate limiters. Now, when you have systems like stock trading platforms, a lot of bots, trading bots, they end up using the platform as well. So I'm sure all of you who are Python developers, you've already probably built your own stock trading bot in the past. When you use these kind of bots, or maybe scraping bots, right? You scrape all this information. A lot of competitors, right? They scrape information from others' platforms. So this happens a lot, at least in crypto platforms. What happens is that you have a crypto exchange, and the other crypto exchange has some, like, is trading at different values, and you're trading at different values. The customers are going to go to the place where there are the stocks are cheaper, the cryptocurrencies are cheaper. So you want to keep always scraping their information, because they're obviously not going to share their APIs with you ever. So you have to integrate, you have to keep scraping their platforms just to be updated with the latest information on their websites. So like I said, there are a lot of bots or a lot of external APIs who may be integrated with you guys who are making too many requests to your server. Or somebody who's trying to use like a Hydra or something to make too many login attempts, like Medusa or something, to make too many login attempts to try to log in, and he's getting failed login attempts. So you want to have a system which says, hey, you from your IP address, you as a user, you've tried too many times. I can't allow you to try this any more time, because you've exhausted your rate. That's called as rate limiters. If you don't have rate limiters, your entire system can be brought down. Like I said, your system can be overloaded with just a few users who can make too many requests in just 1 second. With technologies like Golang, you can parallelize. You can run so many processes in parallel, and you can all of them make a very fast attack on a website, and you can bring them down. So this is why you need rate limiters. The most important concept in system design is CAP theorem. CAP theorem basically says that you can't have all three, which is CAP, all three together. So C is consistency, A is availability, P is partition tolerance. If any of you guys are from the blockchain background, you probably know about the blockchain trilemma, where you know that all three things cannot exist at the same time. So here in Web 2 world, also you have the CAP problem, where so let me go through all the concepts together. So consistency basically means, let's say there are two databases. They are consistently talking to each other. And the two databases, if you make a request to both the databases and they give you back the same information, because they were in communication, right? They were in communication with each other. So when you make a request to them, they give you back the same information, that was the recently written information. And the information is the same from both the databases. That means both the databases or the entire system is consistent. Available basically means if you make a request to the database, it responds back in a given amount of time, like let's say 1 second or 2 seconds. The system is available. That's availability. It returns back data in a given amount of time. Partition tolerance basically means, let's take the example again of those two databases that were in communication with each other. And if the communication breaks down between the two databases and you still make a request to them, they still give you back the same information, the recently written information, which is consistent. That means the databases or the system is partition tolerant. In the sense, even if the communication has broken down between them, they return the same information. They're both they're partition tolerant. So you've understood consistency, availability, and partition tolerance, but you also need to understand that all three CAP cannot exist together. You can't have all three together. So you always have to prioritize. Now there's a hack. The hack is that with microservices, you can decide which microservice can get what priority. You can either have CA or CP or AP, depending on each microservice. Or otherwise, if you don't use microservices, for the entire system, you have to pick one, CA, CP, or AP, one of these three. And only that you'll have to prioritize for the whole system. Okay, so let me give you an example just to make it clearer. Availability, basically like Facebook or Instagram, you always go there, you always want to see it live. You don't want the website to be down ever. Or Amazon.com, they need high amount of availability. Anything that has a lot of payment related information, right? You're making some transactions. Availability is not important. Consistency is very important, because even if the system is down, it says payment failed, sorry, servers are down, like Google Pay tells you servers are down. That is acceptable to you. But if money goes twice or thrice, you will panic, right? So consistency is more important than availability there. Whereas on Instagram, if the same post gets shown to you twice, you don't care, right? Availability is more important, not consistency. So you have to pick and choose based on your system. And we'll do that. We'll also pick and choose based on our system when we actually start going through the board. So microservices, you have, when you start out with any product, you usually have it as a monolith, in the sense you have a UI layer, you have a business logic, and you have a data access layer. And it exists in one big chunk called the monolith. And microservices, basically, you start dividing those monoliths into very small chunks called microservices, where you start dividing the business logic into different parts. It makes it much easier to handle, much more easier to work with. And a great pattern is to give a separate database to each microservice. API gateways. Now, when you're using the microservice pattern, you don't want your front end to go and find or go and do the work of finding which service has what data. So you want to use something called as an API gateway, which is like the single entry point for all the APIs, or the single entry point for the front end to interact with any of the APIs. So it's the API gateway's problem to find out which server or which microservice has what data. The front end just needs to make a request to the API gateway. Otherwise, the front end would become really overloaded. So it's a single point of entry for the client. Now, API gateways don't exist in isolation. Many times, what you'll do is, this is an important point, guys. If you're not paying attention, please just listen to this one sentence very carefully. That many times in API gateways, you might be seeing that API gateways already have a rate limiter and proxy already implemented. Sometimes even load balancers are implemented inside the API gateway itself, right? So load balancers, rate limiters, proxies, all these three can actually be implemented inside the API gateway. But in mostly, like 99% of the systems, you'll see that there's a separate load balancer. And you'll see that rate limiters and proxies might be in API gateway, but load balancer is always separate. Okay, so this is at least what I have seen in most of the systems. Even in the later systems, this is how it happens. People have started using rate limiters and proxies, and they've started rolling that up into an API gateway, just to make things more efficient. API composers. Now, when we have like multiple microservices, a lot of data exists in different services. So you have like authentication information or user information somewhere else, and what the user traded, all his trades in some other place. And you want all of that information together. And since which user did which all trades, you want all of that information together. It's difficult. It's an expensive process. It takes a lot of time. It's aggregation, right? So, aggregation and joins, when you have to join the information, not just from two databases, but also from two different microservices, which have their own databases. And they might be storing information there in their own formats. One could be a NoSQL database. The other could be an SQL database. So that's a huge amount of complexity. And you don't want the API gateway to struggle there. So you use something called as an API composer that does the work, all the pre-work of aggregating this information from multiple services and keeping it in sort of a cache, so that you don't have to actually make those joins in real time. All the joins already happened, and API composers do them beforehand and keep the data ready. So API composers are extremely important. Service registries, when you use, you don't just allot one server to one microservice. In the real world, you use containerization, you use container orchestration, and a lot of complex stuff, right? Container orchestration. With each deployment or with any change or any new microservice, the IP addresses keep changing very often. We know that. But the API gateway won't sometimes know like many of the times it won't know which IP address is the latest IP address for which service. So it will make a request to the service registry. There's something called a service registry. The sole job of the service registry is to take into account what is the IP address of which service. And the API gateway just makes a request to the service registry, gets the IP addresses, then calls the relevant microservice and gets the data. Now you might have this question, right? So if you're new to system design, you might have this question that why do I need a separate thing called a service registry? Why do I need thing called as gateway? Why do I need API composer? Can't I have just one thing which will have all of this? So the answer is no, because all of these have their own underlying data structures and algorithms. They all work in a different way. They all have their own specialization. They're all different technologies. Like load balancer is a very specialized different technology. API gateway is a very specialized different technology. And you want to have all of these things as separate as possible because they'll have single responsibility or separation of concern. Even if your API gateway goes down, doesn't mean the load balancer also has to go down, right? So always think in a single responsibility way of thinking. Don't think that you can crowd everything together and just again make a big monolith, right? So always think that all these things will be separate. Webhooks. So instead of the way we will be integrating our system with external systems, like in our stock trading platform, the way we'll integrate these systems we'll be using webhooks instead of just API integrations, because the information in a stock trading platform, it changes very often. You don't want the external systems to keep making requests to you all the time. Okay, you don't want them to keep making requests because that's basically constant polling of your APIs, and your system gets overloaded. You don't want that. You want a webhook where whenever we have an update, like here we have taken the example of Stripe, wherever we have an update, we send the update to the external service saying that, hey, now we have an update, and this is the new update. This is what has happened. This is the information that you requested for. You need to subscribe to this information, instead of them calling our API again and again to check for new information. Okay, so this brings in an element of event-drivenness, even with our external interactions with external services. So today we'll be learning a lot about event-driven systems. But even before we go into that, I'm just clarifying that even with the external services that we deal with, we will be dealing with them in a very event-driven way. We won't be, just having API integrations. Talking about events, you have the standard request-driven architecture where the client makes a request to the server and he gets a response back. So here the client has to wait for a very long period of time, and so this is like synchronous communication, right? You send a request, you wait for a response. Whereas if you want to get asynchronous, you can use event-driven architecture. So synchronous basically is like having a video call with somebody. Asynchronous or having a WhatsApp call with somebody. Asynchronous is like sending him a voice note. So whenever he has time, he can just look at it. Okay. So asynchronous works better for us because it's non-blocking. You don't have to keep waiting for something. And it can happen really fast, and it supports real-time platforms. So what happens is, like, let's say you have a server which has a new event. So like, let's say there's a trade that happened, a buy or sell order that just happened. And this event needs to be consumed by different other services to, let's say, send an email or send a notification, all of that stuff. And they can simply respond to those events quickly. They don't have to now, keep waiting, keep calling these APIs. We'll dig into this much deeper on the board that I have for you guys. So even if you just understand that there's a difference, that there's synchronous, asynchronous, and instead of calling APIs, we have something called as events now. So here, like you can see, you have events flowing through a stream, which again we'll discuss in a while. Events happen through two things: queues and streams. So with queues, you get ordered data. So you can keep publishing information in a queue, and then you get all that ordered data. You can keep subscribing to it. And usually we use them with workers. So workers are independent programs, parallel concurrent programs that work from the message queue, and then they do a particular task, a very specific set of tasks, depending on what type of event they received on the event queue. So there could be workers who are listening to a specific event. Whenever they get that event on the event queue, they then execute that particular task. That's how this works, basically. Then you have data streams. Data streams are, they process data in real time. So you have sources and you have producers, consumers. Now you don't need to get into all this in depth because today we're just talking about very basic stream processing. You don't have to know the underlying concepts of how something like Kafka works. We won't get into that today, but you need to know that data streams basically work in real time. Now, it's okay if this is not very clear to you. All you need to understand right now in this presentation is that data streams work with unordered data and they work with real-time data processing. And only if this much you've understood, that's okay, because on the board we'll dig down deeper. Producers produce events, consumers consume events. Adapters make sure that the data on the stream is compatible with all the consumers. Brokers basically enable systems to communicate, to exchange information. Like I said, you don't need to understand these. It's completely okay if you don't understand any of this. Just understand data stream has a lot of data flowing through it in real time. Data gets processed in real time. You drive analytics and reports and all of that in real time. We'll dig into that deeper. Now, the big confusion here comes from the fact that if these are streams, what are batches, right? So batches and streams are both going to get used in our system today. So we need to talk about both. Stream processing happens in real time, whereas batch processing happens at a particular time of the day, like 12 p.m. or 1 p.m. or something like that. So with batch processing, you have limited resources. You can use those resources at a particular time of the day to process a lot of information. Stream processing, you can process everything in real time if you have a lot of resources. So like I said, the reason we were learning about streams is because real-time systems, they use streams. So stock trading apps, in our case, they're slightly hybrid. 95% is real-time systems and 5% is request-driven response. So we'll have an element of both in our system design. And real-time systems, especially like stock trading apps, they are near real-time in the sense a few milliseconds of delay is completely okay. They're soft real-time in the sense if the delay increases, it won't hamper anything. It's not mission critical, and it's not at all hard real-time. Now, hard real-time systems are where you send missiles and you have to click on buttons and you send missiles. So they basically, if the delay increases, then the system completely fails. So you can't. It's not a hard real-time system. That's to do with embedded systems and hardware and all that stuff. With us in the software world, we work with near real-time system and software systems. Okay. That's about it. Okay, so yeah, last thing I think is WebSockets. So we'll be using WebSockets to send notifications to the front end. So a lot of people get confused at how does the front end get all those front end or the app or the web app, whatever. How does it get so many notifications or real-time information that's flowing through those graphs? How does that happen? WebSockets are very heavily used in stock trading platforms. Instead of making a request and getting a response again and again, what you do is you just make a handshake, WebSocket handshake, and then the web server can keep sending you data one after the other. You don't have to make any request. So it's asynchronously pushing data to you, like all the notifications of the real-time information, whenever the web server has any update on the information that you're supposed to see. So that's basically your WebSockets. Now let me, so the first part of the system is over. Okay. How are you liking it, guys? Is it good? Okay. Awesome. Great. So it's going great till now. Okay. Some people are saying it's a bit fast, but we have to do that, guys, because this was the basics of system design. We went through it because like I wanted everybody to be on the same page. That's it. All right. So I think it's going good. So everybody's saying it's going good. All right. So what we'll do is now I'll take some quizzes just to understand if you guys understood what I just showed you guys. So let me take a couple of quizzes. So whoever wins this quiz obviously gets a lot of goodies. Yes, by the way, you guys will get that presentation in the WhatsApp group created by Scalar after the session is over, because I have to export that into PDF and I have to send it to somebody who will then send it to you guys on the WhatsApp group. Okay. All right. So the next quiz. So many of you who didn't probably understand things from the presentation, now is a great time to learn from the quiz. You can understand, if you didn't get something right, you'll know what the right answer was. Okay, next quiz. What is a CDN? Nice. So most of you are answering all the questions correctly. Like more than 90% of the people are answering all the answers correctly, which is awesome. That means you guys, this is what I check, before we proceed, I just check if everybody has understood what I was saying till now. So it seems like everybody has understood all the concepts, which is awesome, guys. Makes me really happy. All of you have understood everything. Awesome. Just a couple more quizzes so that we know that everybody's on the same page. Great. Okay, today I think you guys are very smart because more than 90% of the people are answering everything correctly. So we have, I think, a very much more intelligent audience than usual. Awesome. Okay, guys, so most of you got everything correctly. So this is perfect. I mean, yes, Omkar is saying free sessions have the smartest folks. Yeah. All right. So break will be in about like 15, 20 more minutes. We have not even started. We were just doing we're just understanding the basic concepts of system design till now. So we're done with the first part of the of today's session, right? So we're done with this part, which is the 45 minutes learning system design and the 5 minutes of quiz and questions. This break will take about 10 minutes later because I have to give you some knowledge, some information about what we are supposed to do next, and then we'll take a quick break. Okay. Now you have a lot of information now, right? So I will start zooming in to these boards. Now this board, somewhere around 9:30, 9:45, I will give you access to this board, right? After we come back from the break, I'll give you access to this board. The first few minutes, I don't want to give you access to this board because I want you to not get confused. So let me take you through this board so that you don't get confused when I give you the access, which is after the break today. I'll give you the access to the board. So this board has this line, okay? You'll get access to it, but just note that there's this line here, a dotted line. Everything that's above this line is something that will be of immense help to you in all of your interviews in the future. Whenever you plan to give a system design interview, this will be of a lot of help. The information that I've kept here is from a lot of books, a lot of Medium blogs. By the way, you should read Netflix blog, Uber blog. They have their engineering blogs and engineering YouTube channels. So a lot of this information is from those places, right? From very deep resources. Obviously, you're getting all of this for free, so that's amazing for you. But also, you'll always have access to this board, so you can always come back to this board. You can always learn from this. But I'm just telling you that I'll just show you the kind of information you have here. So just about load balancing, load balancers, you have a lot of deep information about load balancers, how they work, like static and dynamic load balancers, how server selection works, categories, benefits, topologies. If you want to get very deep into load balancers, all of that information is here. Okay. If you want to get really deep into scalability, all of that information is here. Like, along with the formulas and all that stuff, right? How mathematically how scaling works. If you want to get really deep into caching, right? So this is almost like reading a book on caching. All the information I have here, it's almost like reading a book. It's the deepest information you might find on the internet. It's not you like it's difficult to find all this, right? I've invested hours and hours onto this. From my own, when I used to study, from my own notes, from all the articles that I keep reading now. So you're getting a lot of value in today's session. Okay, so caching, you get all of this. Like you can go really deep into caching with diagrams. You get information with all these diagrams, how caching actually works. What type of caching is there, and all of these can be a separate interview questions. So I'm just telling you that all of these, how cache replacement works, what are the different cache replacement strategies, how does all of that work, and cache replacement with machine learning, how does that work? All of that information is already here, right? So this is all the information that if you want to go into depth in any of these topics, if you want to go into depth into, let's say, cap theorem, how does that work? So you have that information here. Then you have information about rate limiting. So we talked about rate limiting, but there are so many different algorithms for rate limiting. How do all of them work? I've shown you with diagrams. You don't get this kind of information, guys, on the internet, right? Like with diagrams, you get all this information here. And so if you want to go into depth in rate limiting, into proxies, how proxies work in depth, all of that information is also here. And for advanced reference only, there are multiple advanced architectures like Delta, Sagas, Lambda, and Kappa architecture. All of that is also here. So like I said, above this line is something you don't want to look at. You will, like right now, this is only for your reference only after the session is over, or if you want to prepare for system design interviews, want to go into depth, this is what you want to refer. All of the things that we'll tackle today in today's session will be below that line, okay? Below that line mostly. I think Varun has joined back the session.
I have. Hi, Akhil. I believe you're going on a break.
Yes. So guys, what we'll do now is we'll take a quick break, about 10 minutes. And then I'll see you after the break. I'll stop sharing my screen also, Varun, so that in case you want to
Sure.
And I will turn off my camera. So guys, after this break, we will do all the things below that line which I just showed you. I'm going on a break, 10 minutes. You can take a break if you want.
While Akhil is on his break, hi guys. Okay, I see you soon. I did attend the last 5 minutes. Okay, Bhagwati has an issue. Shri, are you there? So there is, the WhatsApp group seems to be full. If you can just update that, and if the guys don't worry, there will be additional links to the WhatsApp group. Additional groups will be there, so it's not like that. Okay, Akhil's gonna be back in 10 minutes. Meanwhile, what we are gonna do is, I'm sure you would have attended all these, many cohort-based sessions or masterclasses and many other sessions where they ideally do come in and give you a pitch towards the end of the session. We'll not do that. I'll just take quick 5 to 10 minutes to maybe introduce you to what Scalar is, how we do it, what we do, because most of you do also know what Scalar is about, but a few who do not know or who are new, unke liye, for them, what Scalar is, I'll give you a quick walkthrough as to what we do, how we've been, what we've done thus far, and what is the type of dent that we've created in the in the tech landscape of the country. What is Scalar and what was Scalar start? How did Scalar start? So Scalar essentially, as you all know, was founded by Anshuman Singh and Abhimanyu Saxena. Anshuman Singh is the person who was the engineering lead for Facebook Messenger. In fact, the first of its, it was actually something which changed the landscape of messengers. So they had a dream to sort of further India's push towards being the top, being the tech capital of the world, and bringing our pay scales, our basically respect in terms of our capabilities to the top of the world, on par with what the Silicon Valley talent are being paid, or the type of work that they do. And that's how Scalar started. Scalar's full stack engineering program, or something which has to do with the system design, high-level design, low-level design, problem solving, DSA. That is covered in the software development program. And then there's the newly launched data science, which is no longer new. In fact, in September, around October, we'll complete 1 year of that program also. That is for folks who want to make a career in data science. Since we are all here talking about making an app, a developer or picking up developer skills in high level design. The academy program is what we'll be speaking about here. What does the academy program by Scalar include? It's a 10 to 14 month program. It is equally for those who are very new, who ideally have only a few months of experience under their belt as a tech professional. I might not just say as a software developer. Should be a tech professional is what all that is required. From there to even folks who are engineering managers or engineering leads, we've got a scope of including them in the advanced batches. So there's a beginner batch, there's an intermediate batch, and there's an advanced batch. While the offerings, I'm sure there are live classes, there are no record. So recorded classes will be made available to you, but it's ideally live classes whose recordings will be available to you on your dashboard. We'll be coming to the curriculum later, and there, the entire pedagogy of teaching includes one-on-one mentorship, 24/7 doubt solving, and industry projects, open projects in Scalar. Apart from that, the background. Who is this for? Like I said, it's for anyone who comes from an engineering, maths, IT background. QA, if you're a QA, if you're a tester, want to switch, this is for you. All you need to do is clear the entrance test that we have. It's mostly an aptitude-based test with 1 or 2 questions of coding. Even if you don't solve that question, you will still be able to crack the 16 MCQ questions that will be there. Soon after, if you click yes to speak with the career counselor will help you with the entrance tests link. Don't fear, even if you fail that test once, you have 3 opportunities. So don't worry about, or don't take time, you'll need time to prepare. It's fairly easy. It's an MCQ based test, has a lot of aptitude based questions also. All we need to know is whether you have the capacity to learn or not. Here are some outcomes which Scalar has had over the years. The average salary, I'm sure you would all have gone through the KPMG audited report on Scalar's placements. On an average, we've had 94% placement rate. So of every 100 people who've enrolled with us, 94 have been placed. If you have a question, what happened to the 6? There are cases like people don't, happen to complete the program. Okay, the program is not full. It's not a full-time program. The program is a part-time program. You have 2 to 3 classes a week. There are we recently started weekend batches also, if you don't want to do the weekday one. But ideally, we recommend do the weekday ones, because the entire week you are working also and learn, going through the Scalar's course. So that will give you some time on the weekend to sort of have a mental refresher. The highest CTC that we've placed is 1.7 CR, which of course, freshers don't take that package. So average is 20 lakhs. Of course, the highest is 1.7 CR. Lowest would be obviously lower than the average package. But the average hike that we've seen is 126%, which translates to 2.3 times. So imagine, what is your CTC now? If you pass out from Scalar's program, on an average, you should expect making 2.3 times that amount. And the promotion rate is also one very big factor. Of all the people who've passed out of Scalar, we check back with them 1 year after passing out from Scalar in their current, they approximately 30% of people were promoted within 1 year. The average industry promotion is 3 years, like every 3 years or 2 years, if best case scenario. Scalar's alumni see 30% promotion rate. Typical batch profile, again, if you see, it's, I don't know whether you can see, I'll probably speak it out loud. We have 10% of the people who have 10 plus years of work ex, 0 to 50% of the people approximately are between 0 to 2 years. So it's a fairly young peer group, a young learning community. 5 to 10 years again has a 25% share, and 2 to 5 years has equal share. So 25% here, approximately 45% in 0 to 2 years, and 10 plus years has around 10%. Pre-scaler roles, software engineers were around 70%, but there were other IT and other adjacent tech roles also. A solutions architect, a system engineer, those kind of roles. Non-IT business roles also make 20% of the cohort. So it doesn't mean that if you don't have a coding background, you won't make it, you will make it. Pre-scaler salary is also something which you could look at. To give you an idea, average pre-scaler salary was around 8 lakhs, and average post-scaler salary is 21, 22 lakhs CTC. Here's the curriculum. So if you're a non-coder, what is recommended for non-coder is the beginner batch. Join the beginner batch. That also has two parts: beginner complete and beginner refresher. Basis your background. If you are coming from zero, no coding background, recommend beginner complete. Or if you have some amount of have had previous experience in beginners, there's a refresher course that you can join. Then for people who have some amount of basic coding knowledge, they have the intermediate module. Advanced module is again for the folks that I told you who are already software engineers, software developers who are doing it, so they can quickly join the advanced module. A detailed curriculum brochure will be shared with you with your career counselor, who will get in touch with you, or in the subsequent emails that will be shared with you after attending session. Don't worry about it. A deep curriculum also exists on the website. You can download from there. Okay, in the curriculum also there's specialization that you can choose. You can either go for the full stack engineering with backend expertise, or go for the data engineering specialization. Irrespective, career support, placement support exists for everyone. It's irrespective of which batch you join. What is career support? Apart from in helping you with mock interview rounds for the type of company that you want to get into, your LinkedIn profile will be there will be mentoring sessions, there will be LinkedIn profile repositioning sessions, HR rounds, resume. You will be helped end to end. Apart from that, there will be job opportunities also. It's not like it's just training on your interviewing skills, but job opportunity. We've got more than 600 plus employer partners. Like you can see, these are the type of employer partners we have got: Adobe, Google, Facebook, Amazon, Qualcomm, Goldman Sachs. You name it, and the tech company exists. Silicon Valley companies also. How to enroll? I've already told you. Here are a few alumni, and success stories are not 1538. The slide needs to be updated. I'm sorry. We have more than 3,000 success stories, or 3,500 in fact, right now. In the KPMG audit, you'll see more than 2,700 alumni is being placed. To give you a surprise, in fact, we have an alumni who joins us today. I don't know whether you're here. Bhargav, are you here? Give me a quick hi.
Yes, I'm here. Hi.
I can see you. Hi, Bhargav. Very good evening. Thanks for joining us. Guys who do not know Bhargav, here's a quick introduction to him. Bhargav, so essentially Bhargav right now is working with Google. Bhargav, am I right? I'm sorry. Correct me if I'm wrong.
Absolutely.
Yes, so
Right.
Bhargav is now working with Google. Bhargav is an Scalar Academy alumni. He passed out in 2019. Can you believe it? It's been 3 years and he's made the move to the dream Mang company. So Bhargav, a few questions, and maybe that will help give people an understanding. Okay, where was Bhargav working before? Bhargav, I believe you were working with D. Shaw before you.
I think a better surprise for everybody would be before what I was working with Isha. So just tell that I was working with Wipro. Okay. And you might all think, okay, like you would be working in the 10 lakhs per annum Wipro. No, I was working for 3.5 lakhs per annum in Wipro. And now I'm at Google. So
amazing, amazing, Bhargav. With your story, I believe I should also look to, probably change my career, do the course myself. So this is a typical example of, someone having had made a living example of having had made the switch from a service company to a product company, but not just any product company, a Mang company, Google. Quick questions, Bhargav, now to understand, and I'm also unaware of this. The curriculum that you went through at Scalar, do you really see? I mean, see, learning is one thing. I'm sure I know we teach well, so that I'm not asking. But what you've learned, does that come into use in your day-to-day job at Google?
Definitely. I see no place where, like, and Google is something I have recently joined. It's like 3 months since I joined Google. And before this also I was in Disha, and I was there with Disha for quite some time, like 1.5 years. And over there also every day I used to put in somewhere or the other of my data structures knowledge. And no joke, no kidding here, it is all Scalar that taught me data structures.
Awesome, 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 awesome. I can see there are a few questions in the chat. Which stack were you working? Guys, you should probably send Bhargav a LinkedIn request, and then maybe Bhargav can choose to answer, because there are a lot of questions. I don't think Bhargav can take all of these. Bhargav,
Yeah,
another
the
thing
questions
about
are just running. So
I'm enjoying the chat as much as you are. Another question, Bhargav. Um, how did you manage? I mean, assuming you were working on the be it Wipro or DE shop, um, what? How did you manage this? Because I know it gets rigorous, right? So
yeah.
something about how did you manage it, and how did you manage to do so well that Google came recruiting?
So all I had in mind was that I had to see. At the end of the day, I'm doing it for myself. This was the only thing that was pushing me, and I kept saying, like, like somehow or the other, you should make time for this. And like, if anybody can take out 2 to 3 hours every day, like, I think consistency is the key here. Okay, being consistent with working on data structures with Scalar every single day, that's it. That's enough. And Google is no big deal, I would say, because I didn't feel Google interview was that tough. Keeping in mind that I had appeared for tougher questions, tougher interviews as well. And according to me, anybody can get Google interview, Google offer as well. But the only key over here is the consistency that you will have to maintain. You should have the perseverance in you to keep the day, keep all your time, at least 3 hours a day for data structures.
Got it, got it, got it, got it, got it. Amazing, Bhargav. Um, Anything else? I think any of your other experience that you'd want to share here, you would have thought, because we knew you knew you were going to come in and share this with more than 2K folks. Anything that you would want them to do? See, it shouldn't be about Scalar also. Anything that you
Yeah,
took as a motivation, what you did, how you taught, and how do you manage? I think that should also be helpful before we
yeah,
go back to our technical class and hand it back to
sure.
Akhil.
Sure. One thing I would like to say, especially for freshers, because even I was a fresher when I joined Scalar. I joined Scalar with no experience, and within a year, I switched to DShaw directly. And DShaw was not the first company I appeared for. Okay, there were failures in my life before. So all I would say to freshers is that don't get disappointed with the failures that you face during the interview process. There might be people who purposely put down you, like that happened actually to me. Like, don't take it as a disappointment, rather take it as a challenge, I would say. Like, take a breather, train yourself for one or 2 months more, appear for other companies so that you can get experience. And finally, when you're off the cool down period, appear for the company again. In fact, D Shaw, I could not clear it on my first attempt. I appeared in March 2020. I could not clear it. Then again, I kept practicing with Scalar. Then I took another attempt in November 2019. Oh, sorry, 2020. Then I cracked it. So that's what I would say. Like, every success story has got many failures behind it. So you don't have to be embarrassed with your failures. You don't have to get disappointed, dejected about your failures. Just take a breather and keep working on it. At the end of the day, it should be you who has to realize that you are improving on you will have to see the change in yourself. If you can see the change, that's it. Like, trust that change, it will take you to heights.
Got it. Got it. Amazing, Bhargav. Thanks for being here and probably just talking about this. Great, guys. I know you're waiting for Akhil to join back and continue with the session. Just a quick poll. Shreya, if you'll just launch the poll, guys. So there are. I know you have a lot of questions and you want to speak one-on-one with with our counselors. One. Second is there's a chance maybe you want to speak one-on-one with a scalar ALM also. So there's a poll again. I think we'd asked you. I'd shared this earlier in the class also at 8 p.m. Is if you have any more specific questions about joining Scalar or anything that has to do with, because that is the only window you'll have when you can speak one-on-one directly personally. There's a lot of chaos and there's a lot of chatter in chat. We can't take each of your question personally. There's a question from Manish. I can see he says, share an example about someone who joined Google in 2022. Bhargav was someone who joined Google in May 2022. So that's someone. Great. Awesome. Guys, another 30 seconds of the poll before I pass it back to Akhil. Superb. See, it's not like, guys, what you're thinking is the advertisement is happening. That's not exactly what it is. There are folks who've cried foul, have come in chat and said, can you please continue with the session and that. And the next thing that they do is write to me asking, how should I speak with someone, or how should I? See, this is your chance. If you say yes, you will receive a call directly. You don't have to go searching for speaking to someone. So make good of this chance. Otherwise, again, you'll be stuck writing to different people at Scalar and asking them how to join, or I want to join. Or, there are many scholarships also that are available for early bird folks. So that is also one window right now. If you request someone to reach you, within 2 or 3 days, you can, probably get the conversation done. Correct. That's not it, Sagar. There are early bird scholarships apart from that also. There is another poll, Shri, if you want to launch, which is if you want to speak directly to one of our alumni and learner. There are cases, right, when you think, yeah, this could be, paid activity. Maybe we would be paying Bhargav to come here and talk to, or something like that. Could be scripted. We'll take ourselves out of the picture. We'll set up a call between you and the alumni directly. You can speak to them, ask about the truth about Scalar, whether we actually do what we are telling or what we are preaching. Will the curriculum be completed? Will we actually support you with your placements or your mock interviews or whatever we claimed? So if you don't want to speak with someone with Scalar, speak with one of our learners or our alumni, and probably you can see what the truth is all about Scalar. There are people who are talking about the investment being high or time being high. 20 lakhs package on an average, or highest. Let's say talk about highest 1.7 crore as a highest CTC. How will that happen? You go to Stanford, Harvard, you end up paying over 1 CR Indian rupees. The type of outcomes that you're getting from this is on par with that in terms of ROI. FANG job is never guaranteed. Anyone who says you're getting a MANG job guaranteed is faking. It doesn't exist. What is guaranteed is your effort, and that's what will eventually pay off. Okay, my time is out. Back to you, Akhil. You can continue with this session.
Okay, thanks, Varun. Thank you for your time.
Thanks, guys.
All right, guys, we are back in the session. So everybody, I hope you're back from the break. We won't waste much time now. Okay, this session will go on till 11 p.m. Just letting you guys know. So if you want to have a coffee or whatever. Okay, so getting back in. I hope you can see my screen now. I am going to actually reshare it again so that in case somebody had like a pop-up blocker on, please disable your pop-up blockers. I am sharing my screen, like disable your ad blockers, pop-up blockers, all of that, so that you can see my window. I'm sharing it again. Okay. So, okay, sorry, I was supposed to share this link with you guys. So I'm sharing this link with you guys. Okay. Join this link. So all of you guys, I'll expect you on this link now. Please click on it and join the link. PPT doesn't have a link. PPT will be a PDF. I'll share with you in the, Scalar guys will share with you in the WhatsApp group. Okay. So you have the link. In case you haven't followed me on YouTube yet, in case you guys want to learn Golang, Rust, Solidity, Web3 stuff, blockchain related stuff, you can follow me on YouTube. There's videos almost every week. So whimsical access is not temporary; it's forever. There are people who have already, already have access to the board. They know that all of my whimsical boards are access forever. And no, this won't be added as a video on YouTube, guys. This is only a session on Scalar. The reason why this is a session, like a live session, because you can ask me questions or you can learn from each other's questions. On YouTube, you don't get that experience, and I'm able to answer your questions also, which we'll do in the last 20 minutes of this call. Hopefully, this is the session in case we're able to get across all of this content that I have for you guys. So let's get started. We have wasted a lot of time talking about this board and sharing the board and all of that. Now let's actually get started. Okay, so when you start with system design, let's say you have like zero experience, right? You have no context. You're just coming as a junior developer, somebody who has like 6 months of experience. This is the system design that you'll draw. Now, the reason why I'm showing you this is because you can see this, right? And then you'll see where we actually reach today at the end of the session. What I want to do is I want to evolve the system design with, let's say, somebody with 6 months of experience, somebody with 5 years of experience, somebody with 3 years of experience, somebody with 10 plus years of experience. How would they go about system designs? The reason why you want to see this evolved system design is because then you'll understand, what you want to, how much depth you want to go into, depending on how much time you have. Somebody with 1 year of experience, they will just be in like a 15, 20 minute system design round. Somebody with a 7 year of experience, 7 to 10 years of experience, or 5 to 10 years of experience, they will be in like a 30 to 45 minute of system design round. 10 plus years of experience, or somebody who's going for a CTO level job, somebody like that, they sometimes would have 1 hour plus system design interviews, right? So I'm going to show you from everybody's perspective how much complexity you can add. So let's say when you go to YouTube, okay, and you pick up any project, like let's say React and Node.js e-commerce project or something like that, the very basic system design that you draw, then you understand that how systems work is this. Like you would have a load balancer and a forward proxy. You would have multiple front-end servers. You would have a load balancer, a reverse proxy. You have a forward. We've all learned about forward proxies and reverse proxies. So at the server side, there will be reverse proxy, and you'll have multiple backend servers. Each backend server will have its own cache, I've shown here. And then there are horizontally sharded databases, right? So when you have 6 months of experience, this is the kind of system design that you'll draw. But this is not acceptable in any system design interview unless, like, let's say you just have 6 months of experience. Perfectly okay, you can draw this and you can walk out of the system design interview. That's completely okay, right? That you have you're showing your knowledge that you have. I know that I'll use multiple front-end servers, I'll use multiple back-end servers, I'll use cache for every server, I'll use load balancers on the front-end and back-end side, I'll use forward and reverse proxies, I will use horizontally sharded databases. Perfect, shows that you have basic system design knowledge, but that's not enough to impress a interviewer, okay? Now, how do you impress an interviewer? How do you actually start designing proper system designs, right? So the questions that you get around the topic, nobody will tell you to design the entire stock trading platform. We are going to do this. I'm going to do it for you in this session because all of these questions are going to get covered in that kind of a interview, right? In that kind of a system design. So I will, I have taken the pains of actually drawing the entire system design for you guys, which answers at least these 4 questions and many more questions. So for example, when you walk into, let's say, 30-minute round of system design interview, somebody will tell you that, hey, design the system design for a buy and sell order service, or design system design for a stock recommendation service. Okay, how do you recommend stocks? Or design system design for analytics system, design a system for basic crypto exchange. These kind of really basic questions around the topic. Nobody is going to tell you design the entire stock trading platform, but I will do that for you in this session so that you have the answers to all of these questions and many more questions. Okay, so now what we'll do is, what's the first thing that you do when you get a system design problem? So let's say you walk into the system design interview, okay, and then what's the first thing that you'll do? The first thing that you'll do is you'll design something called as the visible trading flows. What does that mean? That means that whatever the user is going to do on the app, that's what you're going to create a flow chart of. So user is going to sign up, going to have referrals, going to have verifications, reset and recovery. He can upload his documents. There can be some manual approvals. In some cases, there are manual approvals. Then there are some bank integration with his wallet where he can keep his cash. If it's a crypto platform, then he can keep his crypto. Different types of crypto, actually, different types of wallets can be integrated. When you have your dashboard, you have your ticker price. Ticker price is basically how many, whatever currencies or what type of stocks are there, what are their prices, that's ticker prices. And then you have transaction history, what all you've done in the past. So in the dashboard, you have transaction history. Now I'm speaking faster, I'm going through it faster because you already have access to this board. So I wanted to zoom in wherever I am on the board. You can look at my screen also, you can zoom into the board also, but you can actually see it on the board. So I can go faster now, okay? Then you have actions, you can buy and sell, you have multiple operations, right? You have the best performing stocks, top new stocks, and you can have searching, sorting, and filtering operations. You can perform basically all these operations. So these are the visible trading flows of your system. Now, as engineers, we know that only the visible flows, that's something that's great for system design, but there's some invisible flows also, which the user does not know are happening, but they're happening at the background anyways. For example, you have, whenever there's a buy order, it goes to a queue, right? So it goes to the buy order queue, and in the queue, you send it to a service which executes the trades for you, and you can notify the services that this trade has happened. You can store that information as well. Similarly, there's a sell queue. So buy and sell are two different things. For a sell queue, you have, again, trade is executed that, you sell this trade or sell this stock, or you buy this stock, sell this currency, or buy this currency. All of that data has to be notified to other services, like email service or reporting service or auditing service, any of that. And also has to be stored. This information has to be stored for historical order information, because every user wants to see what all he did in the history, what all he did in the past. So you want to show that. You also want to inform external services through webhooks. So we've learned about webhooks. We saw that we have to inform external services, and we'll be using webhooks to do that, okay? Then you have recommendation, okay. How does that go? So yeah, so you have pricing algorithm. So every time somebody buys or sells something on a stock trading platform or a cryptocurrency platform, there are pricing algorithms that are taking into account the liquidity of the stocks. So like, let's say on a centralized crypto exchange, you have Ethereum or Bitcoins, and you're selling Ethereum and Bitcoin. So you want to know how much Bitcoin sellers are there, how many Bitcoin buyers are there. So that's liquidity. You want to match the liquidity. The more amount of liquidity, the less the prices, the less amount of liquidity, more the demand, the higher the prices, right? So that's economics 101, demand versus supply. So you want to have these algorithms which are currently tracking in real time all the liquidity of your pools or your liquidity of your stocks, and they're setting the price for all of the stocks, okay, in real time. And based on that, whatever you're buying, you will also get recommendation from various algorithms. Now, these algorithms are getting trained on the recent industry news, the current affairs, and the impending, if there's any crash or recession going to happen or any boom that's coming, they're aware of all of that. So it's all real-time information. Then you're going to have information flowing in from the various stock exchanges like NYSE, which is New York Stock Exchange, Bombay Stock Exchange, NASDAQ, National Stock Exchange, all of that, Singapore Stock Exchange, all of that information comes in. So you can buy this information. You have to buy this information in two ways. One is the APIs, the other is the historical information. When you get the information through APIs, or let's say some information you get in historical data, you want to work with all of this information together. So you would want to aggregate information from these sources. You want to clean up and organize that information because you want to be able to, let's say, show that in graphs and charts and stock indexes, all of that stuff. You want to use that for auditing, analytics purposes, creating reports, all of that stuff, right? Cleanup and organization happens of the data, transformation of the data happens, and storing and indexing happens. Storing, we already know storing is basically storing in database. Indexing, because you want to have searching easier, so that's why you use indexing. So you want to do all that to your data. Apart from that, we are not just considering selling stocks. We're considering that we'll be selling commodities, forex, bonds, derivatives, and crypto. All of that will be selling. So all of that information can go into something called as a stock data service. So all of the information coming from external sources, like the NYSE, all of those APIs and historical information that we have purchased, and the webhook information, all of that is going to flow into a special microservice that we're going to call as a stock data service. It's going to have all the data of all the stocks right now that are getting traded. Then a lot of operations happen on the stock data. You have currency conversions, multiple different currencies, right? Because sometimes what you do is you convert from INR to USD to Singapore dollar to Canada dollar to Australian dollar just to see what's the price in different countries and different currencies, depending on your preference or whatever currency you hold more money in. Some people, they hold money in USD. Some people, they hold more, like NRIs who want to trade on, let's say, something like Zerodha, or Indians who want to trade on Robinhood, right, sitting in India. So we want to know what, like in our currency, what's the price, or in the USD, what is the price. And currency conversions also happens for crypto, like when in Ethereum versus Bitcoin versus Cardano or whatever. Okay, so you have time zones and context happening there. Depending on time zone, what's the cost, right? Or what's the time zone in which these currencies getting traded. And you can cache the currency information. Now, currency conversion APIs are very expensive. So you want to cache that information. You want to, every 1 second or even every 15, 20, 30 seconds, based on how much money you want to burn, you can cache that information and keep showing that old information, like 15, 20 second old information to all of the users. You don't want to call that API every single time a user calls that API. That's very expensive, right? So the biggest hack, guys, the biggest hack to save money in any system, I'm just telling you that answer right away, is to use caches for APIs, external APIs. Whenever you integrate external APIs, don't always, like whenever your users are using your platform, don't call external APIs every time the user makes a request to your system. Okay, make sure you always cache information, keep it ready in your own cache or on your own database, and the user can access that information instead. Do that. Okay, so you get that information in ticker prices, and then you have estimations. So estimations basically mean, okay, so you've done visible trading flows and you've done invisible trading flows, right? These two steps are done. Whenever you're in a system design interview, those are the two steps. You want to do that before you start with everything. Then you want to estimate. Now, estimations, as the name suggests, are estimations or assumptions. You always want to clarify all these numbers with the interviewer. So, for example, in my case, I'm assuming that there will be total number of users will be 50 million in any geography, right? Any geography means any country. And the monthly active users from these 50 million will be 10 million. And daily active users from these 10 million will be 2 million. And concurrent users basically people who are active right now are 200,000. Now you will see a pattern here. You will see a pattern that I'm doing 1 by 5. And from here on, I'm doing 1 by 10, right? So here on, I'm doing 1 by 10. So this is the industry standard for stock trading platforms. Now, because I had a lot of time, so I found out the exact numbers for a stock trading platform, which is that the monthly active users is usually 1/5 of the total number of users on the platform. The daily active users is 1/5 of the monthly active users, and concurrent users are 1/10 of the daily active users. Okay, so I had the luxury of time. I did all this, but this changes from industry to industry. And whenever you estimate any number, you want to check with your interviewer, hey, is this okay? Am I fair in assuming this? So you'll say no. Take it for a smaller scale or go for a larger scale, right? In any interview, you won't see the total number of users more than 1 billion. They won't tell you to design systems for more than 1 billion. That'll be too much. They won't tell you to do that. They'll be like 1-2 million, just design system for 1 million, because that's what they're also comfortable with, right? If the guy who knows how to design system for 1 billion users, he won't be taking your interview. That's for sure. Okay, so what's the average number of buy and sell orders per day per user? So that's 20. So let's say that every day, 20 orders, buy or sell, doesn't matter, 20 orders are executed by every single user. Then what does that mean? That means that for all the users on the platform, which is 2 million users, which is our daily active users. So daily 2 million people, into how many are they doing? 20 orders they're executing. So that becomes 40 million orders they're executing every single day, all the users. Okay. Total, I think this is total stocks on the platform or something. Total stocks getting traded on the platform. So total stocks traded on the platform, we'll assume that's to be 10,000. 10,000 is a big number, but we're assuming that. And every year, we'll have like 4 million orders, which happen in a day. And then 250 days, sorry. So 1 billion total orders. So every day we know that, we have 4 million, right? And 250 is the number of days that the market is open, because you don't get weekends, you get like national holidays and all that. So out of 365 days, only 250 days it's open, and then you get 1 billion, buy and sell orders per annum. And let's say that per stock, the information buffer that we get is 2 kilobytes. So I've shown you what it looks like. It looks like this: ticker name Tesla, price 20, currency USD. It's going to be 2 kilobytes. So what's the bandwidth that we require? We require that 10,000 stocks are there being traded on our platform. 2 kilobytes is the information per stock. So that's 20 Mbps. We need 20 Mbps bandwidth. Okay. What's the bandwidth for buy and sell service? So that is basically buy and sell order per second and into the data buffer size. So buy and sell order per day divided by number of seconds in a day into data buffer size. Data buffer we know is 4 kilobytes. Buy and sell orders per day we know is 40 million. 40 million, and number of seconds in a day is 3600. So that means 4 Mbps. So we need 4 Mbps bandwidth for buying and selling service. So at least we're starting to get an idea about the kind of scale we're working at, right? Now this number and these numbers are not important. At least if you are in a very short, like 30-40 minutes system design round, at least you want to get these ones at least. Okay, don't go for bandwidth and all that calculation. Just do at least total number of users and MAU, DAU, WAUs, concurrent users, all of that. At least do these ones so that you have some good idea, you know. And now this is something you're not supposed to do in an HLD round, but I've done it already for you anyways. This is what the bid looks like. The bid will have, you know, a price, count, bid type, and stock ID. It will have the bid type here will have a sell and buy. So they can have two types of bids, a sell and buy bid. And every bid that a user executes is going to have a price, account, and a stock ID, right? You know, price as in for $40, sell 20 stocks, which is the count, and stock ID, whatever the Tesla stock ID is, TSLA, and sell or buy. And the price ticker, which we'll see on the screen, is going to have a time epoch, which is basically a timestamp. Then you have the price and the stock ID. So this is what you've done. You've done the invisible flows, visible flows, and the estimations. Now, after the estimations, this is something that you can talk about. You can talk about the possible bottlenecks. This is, again, something that you talk about if you are a pro at system design. This is something that you would definitely want to talk about. If you are learning system design and the system design interview is not that important, or you just have like 3-4 years of experience, you might not want to talk about it. It's completely okay. You can skip it. If you have more than 8 years of experience, 7 years of experience, if you don't talk about bottlenecks, you're not getting selected. It's as simple as that. Okay. Bottlenecks basically means that preempting. You're preempting in the planning process. You're preempting where all the issues will exist in the system. Okay. All right. So you have possible bottlenecks, which is basically, okay, so we have, I think I've kept around 7 of these. So first one is that, bandwidth issues. So right now, if the number of orders go up suddenly, so like, let's say, there's a recession going on. So if people want to sell quickly during a crash and the number of concurrent users increases, the bandwidth will be an issue, right? So that's a bottleneck. Charts are generated real time. Okay. So that can be a problem. So there's so many people generating so many charts in real time, that can be a problem. Integrating with various external platforms. Now, when we integrate with external platforms, there are format differences, and there are also failures that happen on the external platform that can induce failures on our platform. Security issues, security considerations. They're a no-brainer. Okay, so money is getting traded, right? So you don't want to. So security is of paramount importance. This can be a bottleneck. Too many network requests between services. So this we'll solve with the help of event-driven architecture, but you want to show this as a bottleneck, that, hey, this can be a bottleneck. Then you want to, there's going to be a lot of big data, right? Too much historical information, as in all the stocks that I will either buy or sell. We have to manage all this data to make sense and use an analytics engine. So we can use data streams for that, but this is going to be a possible bottleneck. Now, the things I've mentioned here, right? These are possible solutions to the bottlenecks. At this stage, you don't want to talk about the solutions, just talk about the bottlenecks. But I'm just showing you the solution that, you can solve this by event-driven architecture, or we can use data streams to do this, and we can solve this. All of that, don't have to talk about it in this section, actually. Then you have metadata for information for each stock. You have images, image processing, and formatting, all of that information required for each stock. So all of that can end up becoming a bottleneck, because image information, images, just the stock information is 4 KB, but image information can be in MBs, right? You have to process the images into multiple formats. You have to format the image like JPEG, MPEG, JPEG, and PNG, all of that. So that these can be possible bottlenecks. So you've done the first 15 minutes. So now it's taken us just 10 minutes, but the first 10 to 15 minutes you can spend in all of this. Spend in this, or even including this, actually spend in all of this. Okay. Now the next stage that you do is you list out all the possible components, modules, and services. Okay. So this exercise that you did here in section 4 and 5, where you drew the visible and invisible flows, you were doing that because you eventually wanted all the list of the possible components and modules. So possible component modules, you'll get authentication, authorization, trading orders, search, filtering, sorting, data formatting, telemetry, notifications, logging, monitoring, metadata service, archiving. All of that information you will get from the flows that you do. That's why those designing those, creating those flows were very important. Okay. Now, when we have information of these possible components, and we have information about, let's say, separation of concern, right? We know that there should be services for every different thing. So this separation of concern. We know that the business logic needs to be scalable. So that's why you need to have multiple services. We can design a naive system, very naive system. Naive system, basically, in many articles that you'll read on Medium, on medium.com, you will see that the author always creates something called as a naive system design. Naive system design basically means that, okay, I don't know much about the system, and let me show you what a bad or a normal, like a normal system design looks like. So once you have, like, let's say 8 months experience or 1 year experience, this is the kind of system design that you might draw. Okay, this is the kind of system that we'll create, where you have reduced team interdependency. You'll have separate deployment and methodologies and frequency. Why? Because what you have done is you have created separate services, like authentication is a separate service. It has multiple servers, horizontally scaled. Authorization service, trading orders as I've shown more servers here because more servers are required for my trading order service. Search service is separate, filtering and sorting. So I've shown separation of concern here. All of those servers are different. Earlier, we didn't have that. We just had like general, if you saw in point number 3, you saw that we had just front-end servers and back-end servers. That's it. We didn't have, like, what type of business logic. Based on business logic separation, we didn't have. But now we have separation based on business logic. We know that authentication servers are different, authorization services are different, trading order servers are different, and search servers are different, and so on. And all of these servers have their own caches here. As you can see, they're all talking to a scaled, sharded, horizontally scaled database. And they have multiple front-end servers. We're using a load balancer this time. We're using 2 load balancers basically, and then we're also using a front-end cache, which is amazing. So this is a naive system design. So earlier we created a system design from the perspective of a 6 months, 0 to 6 months experience guy. Now we're creating system design from the experience of, let's say, somewhere 8 months to 1 year kind of an experience guy. This is what the system design will look like. It's again a naive system design. Somebody who doesn't have a lot of knowledge about system design, but he has knowledge about software engineering, because since 1 year he's been like a software engineer. He knows. He knows solid principles. He knows separation of concern, scalable business logic. He knows that if the services are separate, you have reduced team interdependency. Separate teams can work on separate services. You know that separate deployment can happen for each of the services, and you know that you can have different technologies for each service. So what's happening here is you have, let's say, you can use Python for authentication. You can use, Golang for trading orders. You can use, Elasticsearch and Node.js for search. So for each of these services, you can use different technology, right? So by 1 year of experience, the guy knows all of this stuff. He knows that, I can, by the way, if you already have 1 year of experience, you don't know all this stuff, then you need to change your job. You need to work in a company which teaches you all this, where you get exposure to all this, okay? So you can have separate teams working on separate parts of the software. And most importantly, people with 1 year of experience, they talk a lot about reduced blast radius, right? They talk about how having a separate service, even if that service goes down, it doesn't bring the entire system down, right? So that's why you have the failure is contained. That's called as a reduced blast service. So you apply all these concepts that you learn, of 1 year of engineering, and then you design this kind of a system design. But this is still like this. You can pass with this system design if you have 1 year of experience. Interviewer will say, okay, very good, you have passed, amazing. But if you have more than 1 year experience, you will fail if you draw this in your system design interview. Okay, but why am I saying that? The issue here is that there is no clarity of architecture. Okay, the database is a single point of failure. So even though we have sharded and replicated the database, all the services are still calling the same databases. All the data is still congested in just one place. And there are no separation of types of databases, because I might want to use a different database for search. I want to use Elasticsearch for search. I want to use something else for filtering and sorting, something else for trading orders, and I want to, use different types of scalable technologies like streams and queues and all of that stuff. So all of that has not been considered. So that's why somebody who has more than 1 year experience with this system design, he will fail. So how can you ensure that you create a better system design. To do that, we're going to go through this stage called the 10th stage, which is going to have some information about domain-specific knowledge. Domain-specific basically means that, let's say you are designing for a social media platform. Social media platforms, they use a lot of graph databases, right, to store information. And health tech platforms, they use specific other type of technologies. SQL platforms, they use SQL databases a lot. Similarly, for our stock platforms, we use many different type of things, right? We use many different type of things here in stock trading platforms, and these are all domain-specific informations, right? So, for example, we use time series databases. Time series databases are very, very common to stock trading platforms. So this is why when I said domain-specific knowledge, I meant things that are going to be used very often in stock trading platforms. Time series databases, whenever you go to an app like Robinhood, where you see all those graphs and charts, all that information is coming from a time series database. That means how the stock is performing over a period of time. Like, it was $10 and $12, and it became $9. The way it's changing, the time-based information is stored in time series databases. So it started 1999, and now it's 2018. The most important ones are InfluxDB, are very important. Facebook has done GorillaDB, and you have Timescale. You have Prometheus, is also a time series database. So there are many time series databases that are there these days. Okay, then you have analytics engines. So like I said, we don't have to take the names of specific technologies that we'll be using, like Apache Kafka and Spark Streaming and Druid and all of that. But I'm just showing you here that for our analytics engine, we're going to power off our analytics engines, and we're going to have real-time analytics, and we can do this with the help of Looker and Apache Superset. We can use data from Kafka and Spark, and this is a very common practice. So we'll have to have an analytics engine in our system design. Okay, we can't skip it. Then a very common thing in system design in stock trading platforms is ETLs, because ETLs are basically extract, transform, load systems. So I said that we have to get information from these different stock exchanges in from different APIs. All the information that's coming are going to be in different formats. Some will be in CSV, XML, JSON, blah blah blah. Protobuf, whatever format the data will be. But in our system, for our front end to work, it has to be like one singular format of data. To do that, we need ETL systems. So I'm giving you the example of a front end system right now, but even through our microservices, when they have to interact with each other, they need to basically be talking in the same format. So they're all going to be working with ETL systems. Then we're going to have graph databases. Okay, graph databases basically store information as nodes. So let's say you have a node called Microsoft, and then you have a node called Tesla. So here you've shown that there's a lot of similarity between Microsoft and Tesla and NVIDIA, all of these stocks, and Facebook stock, right? There's a lot of information and similarity between them. Now, the more similarity between them, the depth or the number of lines or the weight between the in the connections between the nodes, they keep increasing. So the more similarity between them, the more the connections between the nodes. Basically, this is how graph databases work. And Neo4j is one of the most common types of databases, graph databases out there. Then you have real-time recommendation engines, where you basically want to use the data that's flowing through the system to make real-time recommendations for stocks. So because somebody is buying and trading with stocks, you want them to have real-time information. Then we'll be using a lot of machine learning engines, because to be able to predict how the prices are going to go up or down in the future, what is the right pricing, the trading strategies, all of that is going to require a lot of machine learning engines. So any of you who have used an app like Robinhood before, a trading app like Robinhood before, that you're going to get predictions, right? Price predictions, which stock should you buy, how is it going to do in the future, and which stock should you buy in general, right? So you have real-time recommendation engines, you have machine learning platforms that help with the pricing, with the price forecasting. Then we'll be using a lot of serverless functions. So serverless functions take away a lot of load from our system by being asynchronous and lightweight and very, very cheap. So the benefits are that they're efficient, easy to deploy, flexible, cheap, and on demand. So they do a lot of repetitive tasks. For example, you have you have AWS Lambda, Azure functions, Google, GCP functions, OpenFast, and you even have serverless databases these days, DynamoDB and MongoDB Atlas, those kind of things, right? So what happens is that they do a lot of heavy lifting for us in architectures like stock trading platforms. And what happens is, let me show you actually. What happens is you start with a monolith application, right? The first example we saw where we just had like multiple front-end servers and multiple back-end servers, that was more or less a monolith application. Then we started dividing into services, right? We had like a separate authentication, authorization service, all of that. But eventually you want to just divide that into small functions. So here, this diagram will have you believe that the microservices transform into functions. It's not like that. You always have microservices, and along with those, to help them with some functions, you have like these functions as services. So these are your serverless functions, which basically which are like extremely scalable because they're not actively taking up any server resources. So you can tell them how much to scale up or scale down based on demand, and they are very good with repetitive tasks. So you save a lot of money. So I told you 2 ways to save money in your system. You save money by caching API requests. You save money by using the serverless functions. Logging systems, in our case, I've just shown you how a logging system will work. So it will not only work at the server level, but at the application level also it will work. So you get logs from different places. You'll get into Logstash, Elasticsearch, and all of that. So you can do multiple things with logging systems. What I wanted to show you here is that every place, like at the server level, at the application level, everywhere they'll be logging. At the database level, infra level, everywhere they'll be logging, we'll be using, right? And the logs basically go into our monitoring system. So I've shown you like real examples of, let's say you're using Kubernetes and Prometheus and all of that, how actual monitoring systems will look like on our system. I've shown you 3 different examples with Grafana, Kubernetes, and Prometheus, how they look like. So you just have clarity on monitoring systems. Now, the most important thing that a monitoring system does is actually send you a Slack notification or a message or an email saying that, hey, your system is down. So that's what it's supposed to do. And it's supposed to create nice graphs for you, which Grafana does. Like I said, it creates nice graphs for you. And then we all know about content delivery networks. They basically help us. So all of the information, right? Like let's say people who want to download reports, who want to look at graphs, but also want to download JPEGs of those graphs when they compare those different stock information. Whatever that static information, like images they want to download and want to look at, it's all happening through CDN networks. CDNs are basically edge servers that cache the information close to the source rather than making a request always to the source server. You store information at the edge servers, and that's closer to the user, so they make requests here and they get the information that they need. Then you have media buckets. Now all of this information, like the images for the stocks and that kind of stuff, the static image, static information that you show through CDNs, basically you store them in media buckets. So for example, an S2 bucket in AWS, you store them in media buckets. So you just had to know all these concepts before you can design a better system design. Now we've already learned in our presentation about API gateways and and service registries. I'll go through them once again very quickly, just as a revision. So API gateways help us help the UI server to interact with different microservices in the backend from a single point of contact, right? And all microservices can have their own databases also. And service registries are basically going to have the IP addresses of all the services that keep changing, their IP addresses keep changing. And this is what I've shown you with service registry, multiple examples, what it actually looks like. Okay. But an API composer, it just gets all the query information, joins them, aggregates them, stores them in cache, keeps them ready. So now let's say you have 1.5 years to almost 3 years of experience. What is the kind of system design that you will create? Right? With all this information that I showed you till now, this is the kind of system design that you will now create. Okay, you will say that there's a user, he has a load balancer, but we're also using a CDN now, and we have a media bucket to store all the images and all that, and we have CDNs to help him download the screenshots or the images of the comparison graphs and charts and the prediction of the prices that he has done. We're going to show him with CDNs. He has a load balancers. There are multiple front-end servers, and there's an API gateway now. There's a service registry now. There are API composers now, which we all know about. Then there are separate servers, which are again scaled, all of the servers. But the big difference here is that all the servers have their own databases now. Okay, all servers, like authentication, users, and authorization. This big module, this is a big module. They have their own server, which is an SQL database. So I'm storing my users' information, authorization information, authentication information in an SQL database, which is horizontally sharded, horizontally scaled. I have my own cache here at the server level side. Then my stocks information order server is a NoSQL database, because I'm going to have to store stocks information of many different schemas, right? I won't always have the same fields for all the stocks. So I'm going to have to store them in a NoSQL database. Then you have a graph database, which I can use really well to create recommendations and predictions for myself through the cache, graph database. And then, just a second. Then you have a cold storage. Cold storage is basically a place, it's a huge database, right? It's a cold archive database where you can store information for backups, monitoring, archiving, logging, and auditing, all of that stuff. And then you have analytics engine, where you use a time series database and use analytics. And this is how you basically create a system design. So the benefits here are, in the system design, the main differences are that now that you have 3 years of experience, you know about API gateways, you know service registries, you know API composers, you know media buckets, you know multiple front-end servers, load balancers, CDNs, you know about machine learning type of prediction engines, and graph databases, cold storage databases, time series databases, caches for server side. You have different types of databases like SQL, NoSQL. Now this is a much better and much richer system design, right? So you have a lot of stuff happening here. A lot of stuff is happening here. But it's not enough. If you have like 2 years, 3 years of experience, you might be able to pass a system design interview with that. But beyond that, it's difficult. So we want to go deeper now. Okay, so now we are entering into the pro zone. Pro zone where the pros, basically pro people, professional guys, they create system designs. They do that by understanding the problems. So all the system designs we've done till now, there's a big problem there. The big problem is, I will show you with an example. Example is, let's say that I have a buy service and I have a sell service. Buy service has to send some data to the pricing service. The sell service, whenever there's a sell that happens on the system, it sends a request to the liquidity service that this stock, reduce this stock liquidity by 1 or by 2 or by 10 stocks. 10 of these stocks have been purchased. And then you have pricing, where based on, like I told you, demand and supply, the price keeps changing. But based on pricing, you have to update prices based on demand. You have to have price prediction training. You have to have analytics. Now the problem is that you'll see these too many requests are happening. So this server needs to keep making requests to this to get some data. This needs to make requests to this to get some data. All of them are dependent on each other. They're all making requests to each other, like API requests to each other, right? So, and they all need to also make, liquidity service also needs to make a request to external services. The problem that's happening here is that too many requests. Okay. Now this is what I have designed for you guys, but in reality, the microservices system looks like this. There are thousands of microservices. When you read the Netflix blogs, you learn about chaos engineering, and there are thousands of more than 4,000 microservices that they have right now currently. Okay, so they basically have this kind of system. It's a huge system, and here it starts becoming a problem, because all of the microservices need to interact with each other. So that's the big problem. The problem is that there are too many network requests. The data formats, you're using structs and JSONs and CSV. You have to do serialization and deserialization of JSON data. Too much latency gets induced. You have to keep polling the APIs. You have failures. You have timeouts, error handling, and wrong responses from different microservices. So you get failures, and you want to recover from those failures, and they're impossible to manage. It becomes impossible to manage so many microservices. So the problem is that stock trading platforms are real-time systems. They should have as less delays, as less latency as possible. And we also need ease of maintenance and security, right? Which we were not getting. We were getting problems, we were getting failures, and getting impossible to manage so many microservices, so much interaction between them. So how to do this professionally? What's the way to do this professionally is something called as a priority planning exercise. So in real world, when you design systems, you get your product manager and your engineering directors and managers, all of those guys, tech architects, all of those guys into one room, and you do something called as a priority planning exercise. What you do is you go through all these considerations. So these are all the possible considerations you can have before you design a system, which are do you want observability? Do you want throughput? Do you want audit tracking? Do you want, what do you want? You want synchronous or asynchronous systems? Do you want stateful or stateless? Do you want high uptime? Do you want high consistency? What do you want, right? You can't have all of these, so you will take only a few of these. So what are the considerations? So you also have security, usability, simplicity, agility, capacity, deployability, privacy, maintainability. There's so many considerations. If you want to learn about each of these considerations in detail, there are articles. So what you'll have to do is you'll have to search. You'll have to go and click on accessibility. You will have to search for accessibility in system design. Then you will read one long article about it. If you want to learn about interoperability, like if you're from a blockchain background, you already know what is interoperability. But if you, or maybe because that's a very common term there for Web 2 also, it's a very common term. That I think so. Not sure. Interoperability basically means that systems can work together very well. So each of these terms, right? You can just go and Google and understand what they mean. We can't possibly go through all of these terms. More than 30 terms are here, 30, 40 terms. We can't possibly, it's not that long a session. We can't possibly go through everything. It's already 10:15, my God. Okay, so we can't possibly go through all of these sessions. So you have to Google all of these and understand them. But I'm showing you what happens in the real world, okay? I'm taking you behind the scenes of, how a really big platform is actually designed. The system for a very big platform is actually designed. You do something called as a Nosql exercise. Nosql basically means from these considerations that you saw on the board, what are your must have, what are your should have, what are your could have, and what are your won't have. So must have in my case, now these things will change depending on whatever people you have in the room with you and what are the business objectives and all of that. But I've just assumed these here for a stock trading platform that you need to have obviously high availability, robustness, high performance has to be there. Recoverability, if failure happens, it needs to be very recoverable. What should have will be simplicity, privacy, and security, definitely, right? Could have, these, now after below this line, right, below this dotted line, everything is like low priority. I could have accessibility, consistency, and localization, replication, cross-check the fees. And I won't have long downtimes and data loss and data hack. So that's my Nosql. That's my Nosql exercise that I do in the real world. Now, this is not relevant from a, you don't have to go in the interview and start drawing all this, okay? So many people get confused. They think that I'm teaching them all this because they have to go and draw this in the system design interview. You don't have to do that. I'm showing you all this because the system designs that you will draw after knowing all this information will be much more refined, okay? This is the only reason that you're going through this with me. Don't take too much stress. Don't think, oh, I need to remember all this and know all this before I go into no, I'm just sharing all this information with you so that you're aware of how the professional people, how they design systems, so that whoever your interviewer is, he possibly will know all this, right? So you also need to know all this. That's basically I'm sharing with you guys. Now there's something called as stretch goals. Stretch goals in a planning exercise are things that you will do once these things are done earlier. If they get done earlier, then you will have some stretch goals, which will, in our cases, that it's cost effective. Our system needs to be cost effective. Like I showed you 2 ways of saving money, which is basically being cost effective. You need to have low latency, maintainability, and reliability. Data, whichever is uploaded, should always reach the database, should not get lost in between. Then you need to have some security considerations. Okay, so for a secure architecture, I've shown you what a privacy as a design architecture looks like. You at every stage you want to have a layer of security. So you want to protect sensitive data. You want to have preventing session hijacking. You want to have input validation. You want to have fine input validation. You want to have protect sensitive data at places. You want to have auditing and logging, authorizing users. You want to ensure only the right users get in. So this is privacy as an architecture, and privacy by design, basically it's called as. So what we'll be doing in our case, we'll be using proxies. We'll be encrypting all the messages in all the messages. I don't mean like chatting messages. I mean all the trading and buying orders. All of those are going to flow through as messages in our system. We're going to have SSL. We're going to hash all the passwords. We're going to prevent SQL injections. We're going to secure the logins, and a lot of the heavy lifting we'll have to do at the server side for cross-scripting attacks. Okay, so I've mentioned that also. So these are our Nosql. This is our priority planning exercise, which included considerations, understanding, Nosql, and stretch goals, and security considerations. Once we have done that, we will come to stage 16. So everybody can come to stage 16. So we've gone through the problem, right? We saw the problem was how will so many microservices interact with each other? That was the big problem. And it was leading to too many network requests. We just saw in that diagram that it was leading to too many network requests. It was becoming very difficult to manage and maintain and all of that. So what is the solution to all of that? The solution is event-driven architecture. So guys, only here with me, you've learned event-driven architecture from scratch, right? Why do we have it? And also using it in the context. So always you'll get easy information about like events and streams and queues, but learning it from scratch as to why do we use it and where did all of this come in from and what are the problems that happen which the event-driven architecture solves, that's what you need to understand, right? So here after this session, you'll have very deep knowledge about system design, about real-time systems and event-driven architectures, because you've seen the problems that can happen. You've seen how system design has evolved, right? So the solution here with those too many requests that were happening and in those microservices is using event-driven architecture. So for real-time systems, we always use event-driven architecture. We don't want to have our microservices making requests to each other and waiting for information. You use queues and you use streams. Queues are used for notifying all the services and coordinating with each other. Streams are used for processing data. And anything that's too heavy for real-time systems, real-time processing, and it's not critical enough for us, that's where we use batch processing. So we learned about real-time stream processing and batch processing in our slides, but now you know where to use what. And our entire system and our entire architecture has to be responsive to events. And our services, our microservices, need to get triggered based on relevant events rather than a request and response. So we won't have a request and response system. You saw that on the slide, right? Request and response versus event-driven. So in our case, it'll be, the services will get triggered based on events. So having thousands of microservices, which we'll have now, it'll become very easy to coordinate and execute important tasks with the help of event-driven system. So the big solution that we are getting is that we have to use event-driven systems. So real-time systems, in our case, which is, stock trading platforms. Now, real-time systems, we have learned and understood in the presentation itself that, in our case, we'll be using soft real-time systems and near real-time systems. We know that much is enough. But in case you want to get down deeper into real-time systems, okay, and you want to get down, you want a lot of detail, I have all the details laid out for you. So if let's say somebody wants to understand, so I'll show you how to go through this graph that I've created for you, okay? So if somebody wants to ask you in an interview, how do you define a real-time system? So it needs to match these criteria. It needs to have precise timing, needs to be highly predictable, needs to be highly reliable. It can prioritize real-time workloads. It needs to have time synchronization between components. Needs to have very low latency, low compute jitter. Okay, it needs to have timeliness. So these are the criteria for it being a real-time system. So I've also identified some really good concepts. So for example, jobs and tasks and deadlines and execution times and release times, response times, resources, all of that is out here. So this is a very, very good resource for your interview time whenever you're appearing for a system, for a company that employs any type of real-time systems. You need to know this. You need to be aware about this, okay? Like for example, if you're appearing for the Uber interview or Netflix interview or let's say Robinhood interview, any cryptocurrency platform interview, you will be asked these kind of questions. You need to know all this. All right. So this is the big connection here, that all real-time systems are event-driven. Now for event-driven system, we've already understood that events are like messages that appear in the system, and then let's say one service wants to talk to another service, they talk using events rather than making requests and responses to each other, right? We look that up in a little more detail in a while, but that's all you want to understand about system. System is like a unit. It is a message that something has happened, like this buy order has happened, this sell order has happened, this guy has logged in, this guy has sold 20 shares, this guy wants to buy 50 shares. All of these are events that are happening in the system, and our multiple services are going to respond to these events, okay? If you want to go down deeper into event-driven systems, you want to know about all of these terms, and I've mentioned all of these terms along with the definitions here in the board itself, okay? So a lot of the work has been already done for you. You don't have to read hundreds of books that I had to read. I won't say hundreds, like more like 10 books that I had to read, and and all the Medium blogs, all of that. So I'm saving you hours and hours of, like, months of time, actually years of experience, because I had to go through all of this experience on my own. So I've saved you years of experience, right, in this 3 hours session. Insane value. Okay, so architectures. What kind of architectures would you use? So in our case, we are using microservices architecture. Like, we want to divide our business logic into multiple parts, and we'll have thousands of microservices. They need to interact with each other. But in case you want to understand about architectures, on my YouTube channel, there is a complete series on tech architecture, and I talk about most of these architectures there. So you can check that out there. Or sometimes with Scalar, we do a cloud architecture session, and that's where also I will cover most of these in a lot of detail. Whatever sails your boat, you can learn about these. But if you want to go deeper into how microservices are created and how we consider about microservices, what are the factors we consider, all of these are very, very big interview questions. In case you have more than 7-8 years of experience, you have microservices experience, you would want to know about all of this, how microservices are considered. Then what are synchronous and asynchronous microservices? In our case, we're going for asynchronous microservices, which are event driven, and they're going to be highly efficient, right? Low number of requests. This is the whole point. We're going to be extremely scalable because there's no limit, because there's no request and response happening, so there's no limit. Super low latency. I've also mentioned the drawbacks for each of these points. Okay, so you don't have to struggle for any answers. All of the answers are on the board itself. For years to come, till you have, let's say some of you guys are at 1 year of experience, till the time you reach, let's say 10 years or 15 years of experience, you can always keep using this board for great answers. You have all the answers out here. Okay. Now, but the problem is that if everybody starts knowing these answers, then the interview questions will start getting even more complex and difficult. So I don't know how to affect that, actually. Anyhow, stage 18. Come to stage 18. So I've taken you through 16 and 17 quickly. That you've understood the solution. The problem that we had was too many microservices, too many requests between them, latency problems, failures, all of that, right? The solution we've seen in point 16 and 17. Solution is that real-time systems need to use event-driven architecture, which can be used with queues and streams, stream processing, all of that. And we use microservices. For microservices, you saw all these considerations, which you will go through. I hope after the session is over, you will take out your own time. You'll go through these points properly, right? And then we're going to stage 18. Stage 18 is where I show you that the big confusion between queues and streams is that queues can be used for messages, events, and data, and streams can be used for messages, events, and data, right? So this is the problem here. This is where everybody gets confused. So when you create a queue, right, you can either use it to transfer messages, like messages means like chat messages, right? But some people also call events as messages, right? But they're actually events. Events basically meaning that this is a buy order. This guy has bought this has sold this, and you can use queues to basically store any amount of any kind of data also. With streams also, you have message streaming, event streaming, and data streaming. So data streaming is like Spark, event streaming is like Apache Kafka. So with queues, you don't have just one queue, right? So many people think that, okay, I'll just use one queue, but that will be like a system failure. No, there are multiple queues. They're all replicated, distributed systems, and you have producers and exchanges and consumers. Depending on which consumer want to consume what, you will get that data. So that's a queue. Streams are basically real-time data is flowing through it here, and data is getting processed in real time. So you have APIs, actions, visual alerts, devices. Now, the real-time processing of streams, if you want to get down deeper into that, I do this session called OTT platforms with Scalar. It's a free session. Feel free to attend that. So there we talk about how real-time data, which is basically the video streaming data, is transformed in real time. In case you want to do that, in case you want to attend that. Now, here's the difference between stream processing and batch processing. With stream processing, in real time, you get filtered, grouped, data. With batch processing, you get it at a particular time of the day, not in real time. Then you have DAGs. In our case, we'll be using DAGs to run these batch operations. These are directed acyclic graphs like Apache Airflow. In case any of you are from a data engineering background, you've used Apache Airflow. Hopefully, you would know that you would use Apache Airflow as batch processing systems to process data. So you don't want to process everything in real time. Okay, that will slow down your system, and that's a bad strategy. The heavy stuff you want to keep it in batch processing, and the light stuff you want to keep it in real time processing. Now there is a hybrid called micro batch processing, which is like real time, but you're also doing the work of batch processing. So you're doing both of them in a hybrid way. Spark can kind of do that for you. So along with DAGs, we can do that in micro batching. So micro batch processing is like doing everything in real time, but instead of just taking up light data, you have data in micro batches instead of a big batch. In our case, we'll have API integration buses where we'll do some API-based automation, because we're working with so many different APIs. We want to have a bus which standardizes all the information, all the data for us from different APIs. Then we'll be using column-based databases for backup. We'll be using archives for now. Stock trading platforms are very vulnerable to attacks and problems, right? And people also keep filing a lot of cases against them. So they have to go through a lot of compliances. So they need to archive all of their data, all of their stock trading information. They need to archive it basically for audits with governments later on. Now, having known all of this, there are about just like 4 or 5 more points to go. 4 or 5 more points to go. And then we'll actually design the final system design together. We'll go through it. So this will take us about 15 minutes. And before that, we need 15 more minutes to go, like not 15, but 10 more minutes to go through all this information. Why are you getting this whole big bombarding of information? Is because you need to understand all of this information to be able to design a better system design. Like I said, this is a complete system design. You will never be asked a question like design a complete stock trading platform. You will get a small problem here. So you may have to draw only this part of the system, But I have done the whole thing for you so that you have complete clarity on how the entire system in entirety works at the same time. Okay, because you will get just 30 minutes, right? But when you have so much of context and so much of information and knowledge, you'll work in a much better way. All right. So let's quickly go through all this. Now, stock trading platforms, they have something called as multi-tenancy, where multiple, let's say there's a company called IBM. Then they want to do some stock trading on Robinhood app. So, and there's a company called, Wipro. They also want to do some trading on the Robinhood app. Though there will be many people sitting from on behalf of IBM and on behalf of Wipro, right? So they will need a multi-tenant kind of an account where they have a company account. Where in the company, there will be multiple people. So multi-tenancy basically means that there will be multiple people from one tenant, from one company using it. So you can either give them one database, or you can have a shared database between them, or you can share the database but have separate schema. But the best pattern is database per tenant, where you have a separate database for separate companies. So IBM gets their own database and Wipro gets their own database, so that whatever stuff they're doing, it's only accessible to their employees. And if everything gets deleted, it doesn't affect what Wipro was doing. Okay, so here I've shown you more different patterns of that. Like I said, apps like cryptocurrency trading platforms, they are highly competitive. They have a lot of competitors. They are highly, like Binance is competing with some other exchange. They're not going to integrate APIs with each other because they're all selling the cryptocurrencies at different costs and different prices. So they're going to have distributed crawlers. Now, this is a very common practice. Many people get very, very astonished when I share this with them. All these companies they use distributed crawlers to crawl different websites. This is a very common practice in e-commerce also. E-commerce websites like Amazon and Flipkart, they always have their crawlers on different websites to know how much that they're selling, that how much that, let's say, an underwear is getting sold on Amazon and Flipkart guys, they need to know in real time all of this information, right? So they can change the pricing on their website. So this is a very common practice, guys. And this is happening in the crypto and the stock exchange world as well. So you use distributed scrapers to get information from across your competitor website into something called as a data lake. Data lake is where a lot of huge amount of information exists in at any given point of time. Okay, you're not storing this information or persisting this information for long-term storage. You just have it available in a data lake so that you can process that information. So data lake is different from a warehouse. In a warehouse, you store information, you persist information for a long period of time. Data lake, you just have information flowing in a place where you can process it in a better way. So these days there is a new concept of lake house, which is warehouse plus lake, which is data lake house. You can do lots of stuff here. You can do BI, business intelligence reporting, and data science and machine learning algorithms, and you can get a lot of business insights from here. So this is warehouse and auditing. So you want to store all this information in warehouses to be able to create reports and to be able to create to be able to use it for auditing. Then the trading. So sometimes when you use platforms like Robinhood, you can set when you want to sell a particular stock or when you want to buy a particular stock, right? You don't want to take a big loss. So you have these rules engines, which is like a standard rule engine sitting on some server, but all the users can use it and they can set their own rules. Sorry, whenever this whenever this stock is going this much down, you can sell it off or you can buy it. So I just want to tell you that rules engines are a very common thing in stock trading platforms. Then you have algorithmic trading and bots. Now, many third-party bots are integrated with our systems, with our systems, and they do a lot of bot like trading. Also, there are first-party bots wherein our system, like let's say our platform, also like if it's Binance or some famous crypto exchange like that, you can. They also give their own bots sometimes that, if you want to automate everything, you don't want to worry, you want to take those trades on your own, because cryptocurrency markets are 24 hours, right? So you want to automate all of that. So you use algorithmic trading bots. I've shown you here system designs of bots in case. So this is another question. So somebody can ask you, let's say you're going for a Web3 company interview. They ask you design an algorithmic bot or design a crypto bot. System design. This is the answer for that. So all of these stages that I'm taking you through, like do a system design for rules engine, do a system design for data lake house, do a system design for algorithm trading bots. You have all of that information here on this one board. How do price prediction algorithm services work? Do the system design. You have all of that here, guys. All of that is here available to you. This is how price prediction algorithms and services work. We just have this diagram here because we want to be able to utilize that in our final system design. And then we have something called as micro front end. So let's say you have, React developers are very difficult to find. So you have some guys who are Angular developers, some guys who are Vue developers. With the help of a micro front end framework, you can get them, all of them, to develop in their own technologies and have the micro front end framework show that information because they're all component based, right? So somebody can develop a component in React, another guy can develop it in Angular, and a micro front end framework can show all of that information, and the user doesn't have to know that they're all built in different technologies. So having learned all that, now is the time to go through our final system design. Now there are two more topics here, which is to do with distributed systems, right? I won't go into that right now. This is so, by the way, I take another class with Scalar called Distributed Systems. It's a free class again, if you want to get very deep into that. This is not the stuff from that class is like very, very advanced, but this is just some stuff that you might want to know. But I'll talk about it in a while. I'll take you through the system design, and I'll talk about this also a little bit so that you have at least some little bit of context about what all that is. Anyhow, let me also check the chat, what's happening. Okay. The chat is mostly spam, guys. You're not like writing anything useful in the chat. Like I thought you would have to have like some questions in the chat. Yeah, I don't see any questions in the chat as such. All right, so I think everything is fine with you guys. So are you guys enjoying the session? Can you give me a yes if it's going great for you guys? Awesome. Okay. So some of you are saying no, I think, because there's a lot of information and it is difficult. But that's how it is, guys. It's a huge platform. It's difficult. Okay. Awesome. So everything looks good in the chat. Okay. Now what we'll do is we'll start getting into the actual. Yeah. So some of you are a little overwhelmed. I can see that it's a lot of sessions. So some of you are saying that it's too much, too fast, too much information, getting overwhelmed. But that's how it is. It's one of the most difficult. It's one of the most difficult system design problems, guys. Okay. Okay. So let's get into the final system design. So some of you who are saying they didn't like the session, guys, I know it's a lot. I know that's why you probably didn't like the session. I know it's a lot, but I request you to then attend this session. This session does repeat once every 2 months or so. So do attend that repeat session so that you'll understand that in the second go. It's always possible that in one go, not everybody will get it. I completely understand. So if you're not able to understand it, please join it 2 months back. Like 2 months from now, it'll repeat, and please join it then. All right. So and obviously there's no reason to not like the session because it's free. You're getting all this information for free. So if you're not liking the session because it's too much information, I mean, who says that, right? Who says there's a lot of there's too much awesome stuff for free? I don't like it. If you're one of those guys. You can just attend the session again 2 months from now. Okay. All right, so we have now our final system design. We'll be going through the final system design now. Now that we'll go through this, you'll have so much more context and knowledge and information that you'll be able to understand all of this at the same time. But like I said, you're not expected to design this kind of a system. But I'm doing it because this kind of solves multiple problems for you guys. Solves multiple different, like multiple different problems, system design problems. The answer is in this system design. So you have these multiple guys who are multiple traders who are sitting in edge locations, and then you have your CDNs at different edge locations, and then you have your what do you call it? You have your your micro front end framework, your front end servers. It's like a server farm, right? Front end server farm. So your front end is connected to your back end with APIs also, but with socket also. So you have a socket connection, as you can see here. It's connected to these streams. So streams are like the backbone in this entire system design. So there are multiple streams, and they're all distributed and replicated streams. It's not a single stream, right? So there's no single point of failure. There are multiple streams like these. And then you have a bucket, and then you have a read-through cache. Okay, so bucket we already know is going to store information like the image information and the logo information of all the stocks. The read-through cache is going to have some information for the front end, like if this was this guy, what all permissions does he have? What is this guy's token, like authentication token? All of that can be in the read-through cache. Then we have some Redis cache for our sorting and filtering. So I'll talk about that in a while. First, let me zoom in here. This is the heart of the entire system, right? This is the most important service, which is our stocks, data, and price microservice. Okay, and so we'll come to this in a while. But all of these services are interacting. They're all connected to the streams. And when you see something like this, right? When you see these two arrows here, that basically means that the microservice is producing events and also consuming events onto the stream. So like I said, the front end is connected to the streams using socket, but it's also going to hit the API gateway. We already know that API gateway already has a proxy and rate limiter. All of that is already built into the API gateway. The external systems that interact with us are also going to hit our API gateway. They're going to be connected with webhooks for third party. all the traffic goes then to the load balancer from the API gateway. That goes to your service registries. There are multiple service registries I can see. Load balancers can help divide traffic between them. And from the service registry, it first goes to the authentication microservice where the user gets authenticated. Then you get authorized, where you come to know how much permissions this user has. Then he starts interacting with the stocks, data, and price microservice, which is like the most important microservice here. Now, each microservice that you see here has multiple servers. The microservice itself has a load balancer, a cache in the beginning itself. You have a cache here because you don't want to always hit the servers, right? You can get the information here itself. You don't want to always hit the databases. You can get the information here itself at the database level cache. So this is how each microservice is structured. Now, the stocks and price data can be used by Elasticsearch for searching. It can be used for sorting and filtering, and the sorted and filtered data can be stored in a Redis cache. It can be like this. Data comes in from data lakes, right? Data lakes, like I said, you integrate with multiple APIs like New York Stock Exchange, all of that APIs, and we are pulling in some information from different stock exchanges and different RSS feeds also into a data lake. From that, we queue the data, raw data onto a stream. Onto a stream, we perform some extract, transform, and load with the help of ETL systems to get the data into a particular format. This ETL and transform data is going to be used by real-time analytics engines, which is going to create our dashboards, charts, and graphs for the users. We'll have separate functions of the service, like fast functions running to create downloadable JPEGs from chat information. Then we are going to what are we going to do with that data? Just a second. Okay. Then we also, from this main streaming cluster, we also are powering our monitoring service, which is going to check the logs at each point of time. The monitoring service is a small service, has only 2 servers and a database and a time series database mostly. And it's going to push the notification set of triggers in the infra wherever new scripts have to run to build new systems and build new containers, that kind of stuff, create new builds. All this information, this information can also be consumed by trading bots, which can be supported by the platform or not, or some external ones as well. I've already talked about the rules engines and the anatomy or the system design of a trading bot. Also, stock trading algorithms, they get trained on a lot of data. You get trained on data that's coming in from multiple scrapers on data streams, and you have like machine learning engines to tell you how the stock trading platform should work. We can keep training them. Then you have a separate queue where a service for sending data to the outside world, the other systems that need to get triggered when something happens on our system. They need to be notified. All of that's happening through webhooks here, as you can see. There's a separate service that only takes care of interacting with the external services. So, and there are these fast, fast functional services, Lambda functions that get triggered. They send stuff on the message queue based on whatever is happening on the mainstream, whatever is happening there. It goes to the message queue, and from there on, you can send emails saying that, hey, yesterday you bought this, you sold this, or you have authorized this much trade. All of that stuff happens here, notifications and emails. What you want to do is you want to keep pulling in or extracting data from all the databases, from all the microservices. You have a data ingestion pipeline, and you push that onto a data stream. Now, this data also gets extract, transform, loaded into a single format, and that raw data gets processed, prepared, and you create dashboards, charts, and reports, like long-term reports, right? As to what's happening on the platform. You store that in time series database, all the stock related information. You store that in archives because you want to keep auditing that for future purposes. And you also use machine learning engines, which can predict trades for you better, or predict the prices for you better. This is the entire system design. Now, it doesn't look very complex now because you have so much context and you've gone through the entire session with me, which took about 2.5 hours. Like I said, the link will always be with you guys. Keep revising, keep coming back here. It's a lot of information to take in. I know that, but I never said it would be easy. All right, so Just a reminder, in case you're not following me on YouTube, you should follow me on YouTube. All right, so let me now take up some questions from the questions tab. So Ranjit Sahu is saying, will we get notes for this lecture? Yes, Ranjit, you have already got the whimsical board for this session, and you will also get the PDF for the system design PDF presentation that I showed you. So Abhishek is saying, do we need 3 hours for this session? Abhishek, yes. I think by now you also agree that we needed 3 hours for this session. Okay, so Priyansh Shah is saying, can screen sharing resolution be improved for your side? Priyansh Shah, I'm using a capture card, an Elgato capture card, which is streaming in 4K. My camera is a 4K camera. I'm streaming in 4K. My screen with the capture card, 4K capture card. My audio is, as you can see, is 4K audio, like whatever. So the screen resolution problem has to be on your side. It can't be on my side. All right. So what are the prerequisites for this session? Tejas is saying. So Tejas, prerequisites. Yeah. Okay. You asked this 2 hours back. So now it's too late for this question. So Aditya is saying, are we making a stock exchange prediction model? Aditya, that's a very specific machine learning problem that can be tackled in a machine learning session. This is a system design session. You don't have to make a stock exchange prediction model. Okay, so Tilak is saying, what is system design? I'm a complete beginner. So I hope by now you know what is a system design. Okay. Okay, so Ashutosh is saying, in the past, I've made crypto exchange, and the major problem I faced was with the matching queue or matching engine. I would love if you could address this issue in today's session, as the trading volume per second is too high and running. Yeah, so Ashutosh, that's a great question. You're right. But I think you're talking about a centralized crypto exchange where you have to match the buyer with the seller. Now we have dexes where we have liquidity pools. We can, the smart contract can buy, as in you can sell to the smart contract, and smart contract can hold the liquidity pool, and then people can buy from it. You don't have to do all the matching queue, matching engine problem anymore. Okay, so Prathamesh is saying, how is the cost estimated for such a highly scalable system? How to calculate the cost of systems? Can you answer this question? So Prathamesh, you won't be asked to calculate the cost. I think you're saying cost of building it, right? So cost of building, in case if you're really, really curious, you'll have to estimate how many engineers will work on it, how many cloud architects, and what's the cost of your AWS or cloud service. All of that has to be factored in. But I'm assuming this will be like in hundreds and thousands of dollars per month to operate. So Rahul Kumar is asking, what is the difference between API gateway and load balancer? So Rahul, I will be sharing the presentation with you, and this question will be answered there. You don't have to worry. So Santosh Kumar is saying, is this stock market analysis class? No, Santosh, it is not. Subhajit is saying, WhatsApp group is full. How do I get notes? So Subhajit, the scalar guys will take care of that problem for you. Okay, so Shreya is there on the call. She will take care of that. She will make sure you get the notes. Okay. So Tarun is saying, questions to be asked to client before system design, best books to go through, any other learning sources, how might take it to, okay. So I think, Tarun, you mean questions to be asked to the interviewer before system designing the system, right? Questions you can ask him about estimations, about, actually, yeah, about the numbers. You can ask him that how, for what kind of scale do you want the system to be designed. And best books, there is a list of books that I can send you on the WhatsApp group. Again, you'll get it. I will send you the list of books that you can go through. Sources for learning system design. Yeah, go through the Netflix engineering blog. Go through the Uber engineering blog. Awesome stuff. Go through, search for system design on medium.com. You'll get a lot of stuff there. And how to take it. How long might it take to get to an intermediate level? It's on practice, Tarun. The more you practice, you'll get there faster. Anurag Pandey is saying, what language is used for system design? That's not a relevant question. Prabhat is saying, can you suggest some system design books? Prabhat, yes, I'll be sending you that in the WhatsApp group. Bahubali is saying, please share the PPT. It will be very helpful. Yeah, I'll be exporting it into PDF and sharing with you. Kishore J is saying, hello, Akhil, you speaking like shooting arrows on a random targets. Yeah, so some of you, some of you people are stock traders or UI UX designers, and you won't understand anything in the session. I think I clarified that there. So anybody who's here for stock trading, I'm sure you dislike this session. You didn't understand anything here. But what can I do? It's a confusion on your part. We thought this is a stock trading system, whereas like stock trading course, but it's actually an engineering course. So Ishita is saying, Ishitwa Agarwal is saying, is sharding